For lesson 12.4, we're going to begin a very important section where we're going to find that we'll need additional tests to determine if a series will converge or diverge. Very often the integral test will not be as effective. You won't be able to find antiderivatives. And sadly, p-series won't obviously be present in every single series we'd have. That would be rather silly, honestly. But let's have some review of the p-series right here. If you had 1 over n to the p, as we talked about in section 3, this series we could quickly say will converge if that power exponent p is bigger than 1. Similarly, that p-series would diverge if p is less than or equal to 1. Well, our series today will look a little bit different, although, and this is very, very important, our series will look incredibly close to p-series or geometric series, something that we know about convergence or divergence with a little bit of work. So we're going to learn two tests. You can see at the top of the screen, I can use the basic comparison test to tell if a series converges or diverges. And I can use the limit comparison test to tell if a series converges or diverges. Let's talk about the basic comparison test first. The basic comparison test says, let's say that we have two series, a sub n, the summation of that, and sigma b sub n, and they're positive term series. Everything today is positive term series. We can say that b sub n, the summation of b sub n, converges, and if that is true, if we know that to be true, and a sub n is less than b sub n for every positive integer n, so each corresponding term, like a of 100 would be smaller than b of 100. If that is true, we can say that the series a sub n converges also. And I think a visual could definitely help you out. Take a look at this picture right above. I've quickly plotted out a picture with some color. B sub n is the series that we know would converge. So in other words, in blue, we have a listing of partial sums. And, as we add up 100 terms, add up 1,000 terms, or whatever it may be, we'll begin to see that those partial sums begin to level off, and they'll get closer and closer to some real value, some real number, which we could call L. Now, if a sub n is smaller than b sub n, term by term by term, that means its partial sums must also be smaller than b sub n. So a sub n in partial sums would be in red stars, and you could see its partial sums are going to be leveling off as well. They're going to have to level off. They're not going to have the freedom to shoot off towards infinity because those partial sums in red are smaller than the partial sums in blue. And if the partial sums in blue for b sub n level off, it forces a sub n to level off as well. That's really the big idea of the basic comparison test. There is another side to it. Look at Roman numeral 2. Let's just say that you have a series b sub n, but this time we say that that series diverges. And a sub n is actually bigger than b sub n, term by term by term. We can then say a sub n diverges. So where we're going with this is this second picture off to the right. Let's just say that we know that b sub n diverges. It's a positive term series. So to say it diverges means that our partial sums are not going to level off. In blue, here are our partial sums. They're shooting off towards infinity. But if term by term by term, a sub n is bigger, that means the partial sums for that series of a sub n must be larger as well. So these red dots would indicate the partial sums for the series involving a sub n, and they must be bigger than b sub n. If the blue dots are heading off towards infinity as we move to the right, surely the red dots would as well. And that would be why we can say a sub n diverges. It's important to notice that this relationship for both of these cases must hold true. If I know, for example, that B sub n diverges, that it was launching off toward infinity, but if I would have had that A sub n was smaller than B sub n, the red dots would have been below, we actually couldn't say that A sub n would diverge. The red dots being below, who knows, maybe they'd level off. In a similar way, going back to our first case, if I know that B sub n in blue levels off, but if A sub n would have been bigger, that means that the red stars would go above these blue dots. Those red stars possibly could be heading off towards infinity. So it's very important to note that when B sub n converges, we use the basic comparison test only when our A sub n series is smaller than the B sub n. That's that first picture. If the blue partial sums are leveling off, it forces the smaller partial sums, the red ones, to level off as well. And by way of comparison, taking a look at number 2, if we knew that B sub n diverges, it's launching off towards infinity, we would have to know that A sub n would be larger, and then we can say that A sub n, that series, would diverge. Before we move on, I want to state something that might seem almost obvious, but and I certainly don't mean to insult anybody's intelligence, but we must talk about this because the following reasoning is going to be employed for all of these problems. Consider a fraction c over d. If the numerator were to get larger, were to get bigger than it was previously, your fraction obviously gets bigger. If your numerator gets smaller, then your fraction gets smaller. Guess why we're stressing this so much about talking about when we're bigger and when we're smaller? That's very important in the basic comparison test. We need to know which terms are bigger than the others. And by way of comparison, if you change your denominator, the larger a denominator gets, you're going to see that your fraction gets smaller. Look, compare 1/2 to 1/3. You can quickly see 1/2 of a pizza is clearly more pizza than 1/3 of a pizza. So the bigger that denominator gets, the fraction has a smaller value overall. By way of comparison, if you make your denominator get smaller, your overall fraction gets bigger. Well, it's great to be able to talk about that. But now let's actually use the actual basic comparison test. Let's consider A sub n to be n all over 5n squared minus 4. We're going to let A sub n be the original series. So, as I'm investigating this right here, we can more or less say that we've got A sub n. But I guess what we need to do is find a nice way to make a comparison. Please hear this. This might be the most helpful part for both the limit comparison and the basic comparison test. Look at your original series and the nth term of it especially. Try to see a hidden p-series or a hidden geometric series by losing or adding an additional value. So when I'm looking at this n all over 5n squared minus 4, we're going to consider b sub n to be, how about we just lose the minus 4? Truncate that minus 4. And why? Because now I'm left exclusively with variables. Real quickly, we can say, well, that right there is going to have the n's cancel, and very nicely, we'd have 1 all over 5n. Now, at this point, you have to ask the question, we just made a decision to lose that minus 4 because now we have something much more simple. We have this series that we could discuss and we could talk about. But I guess what I'm trying to get at is, did we make our denominator coming right over here when I lost the minus 4, did I actually make my denominator get bigger, or did I make it get smaller? Well, losing that negative 4, not subtracting 4, I hope you would agree our denominator actually got bigger, right? If you're not subtracting the 4, your denominator gets bigger. Look at what I just wrote up above right here. If your denominator gets bigger, your fraction is smaller. So I can say b sub n is actually going to be less than a sub n. B sub n is actually less than a sub n. A sub n is going to be larger than b sub n. But as we look at b sub n in a series, we've got this 1 over 5n, which, by the way, I could factor out a 1/5. You could always factor out a constant. And this diverges by the p-series. Or you could even say that it diverges because it's a harmonic series. Now at this point, guys, I hope you're looking at this and you're saying, okay, so b sub n diverges. B sub n is going to be launching off towards infinity, and yet a sub n is larger. Let's take a look at this picture again. It's the second case. B sub n is in blue. That's that harmonic series. It's launching off towards infinity. A sub n, term by term by term, is larger. A sub n has to be even larger than b sub n as you sum them up forever. So what you can do is say, by the basic comparison test, the original series diverges also. Okay, so a really nice kind of a follow-up right there. Let's please realize that the writing out of this is actually required, guys. It can get a little irritating at points, but this is really a proof, much the way that you've proved things in the past in geometry and doing trig identities. You want to describe what's happening with this work. Okay, so I'm going to stop the video here, and we will pick up with example 2 and then lead into the limit comparison test.